supplemental lecture. I think this will be the last one. All I want to do today is cover the end of lecture 10 with a few problems, one on Norton analysis and another two on op amps. Okay, this for me is slide 44. Given the circuit here, which has both a voltage source and a current source, and both of them are independent, which is a good news because we are asked to find the Norton equivalent, which means that to find the input impedance at terminals A and B, we need to disconnect those sources. We get to disconnect those sources. So let's do that. This is going to be the circuit that we will be analyzing to find the input impedance. Okay, so I'm going to short the battery and I'm going to open circuit the current source. Actually, let me do something here. This will be my 8 ohm resistor. This will be the combination of the 1 ohm and the minus 3J capacitor. Okay, so one thing that may be confusing to you is that we don't actually consider a was between A and B. We take that out for the Norton analysis. We're saying if you were looking from terminals A and B into the circuit, how much impedance do I encounter? So I don't have to worry about anything that's between A and B. And then I'm going to put in my loads here. 8, 1 minus J3, and 4 plus J2. So this is just an exercise in impedance combination. And so you can write ZTH as the parallel combination between this branch and this branch. So that becomes the bottom branch I'm going to write as 9 minus J3. And the top branch I'm going to write as 4 plus J2. And that becomes, as a fraction. Let's see the easiest way for me to write the fraction here. 9 minus J3. Or 4 plus J2. And what I do is I multiply the top and the bottom by the conjugate. And the result, which you should verify for yourself, is that ZTH equals 3.18 plus J 0.71. So this product on the numerator and denominator of Cartesians, you will convert to a polar, and then dividing polar numbers is straightforward, and then you can convert back into a Cartesian if you want, or leave it in polar form. I have converted it back to Cartesian here. All right, so now the more involved step of finding the Norton current. So here's where we have to put back those sources. So we're going to redraw this circuit, but now with, I'm actually going to see if I can make use of, yes. The current source, and we have our battery. This is 20, and this can be written as negative 4J if you want. because 4 with a polar angle of -90 is just 4 pointed down the imaginary axis, which is -4j. Okay, so the question is, how do we solve this? Well, you probably may have guessed that this is well set up to do mesh analysis. So our 3 meshes are going to be here, here, because for Norton analysis, we will short circuit A and B, and I3 is going to be here. So now what we have here is a super mesh, right? And so this here, this mesh contains a current source common to the 2 meshes I1 and I2. So what we're going to do is write KVL around the super mesh. That will give us -20 plus 8 times I1 minus I3 plus I minus J3 times I2 minus I3. And that's it. That's the KVL around the super mesh. And that will simplify to, let's see, 8I1 plus 1 minus J3 I2 plus, this is going to be -9 plus J3 times I3 is equal to 20. Make sure I copy those right. Yeah. That's equation number 1. So KCL around the super mesh, at the super mesh, it's pretty straightforward. We have I2 flowing in here, so we're gonna be applying KCL at this node here. We're gonna, let me see. We're gonna be applying it at this node. And our super mesh equation becomes I2 flowing in is equal to I1 flowing out minus 4j. And so that can be written as I1 minus I2 is equal to J4. Just make sure I got that right. I believe I did. Okay. Then lastly, KVL around mesh number 3. So we're going to go clockwise, starting at the bottom left here. So we're going to have 4 plus J2 times I3 plus 1 minus J3 times I3 minus I1 plus 8 times I3 minus I1 is equal to 0. Make sure I get that right. Oh, see if I can cut this. I2. So 1 minus J3 is multiplied by I3 minus I2, not I1. Okay, and that simplifies to -8 I1 plus -1 plus J3 times I2 plus I3 times 13 minus J. Make sure I got that right. -8, -1 plus J3, and that's equal to 0. And so when you solve those 3 simultaneously, you obtain a value for I2 of 8.39 angle negative 32.68. And I2 corresponds to IN. That's important. That's equal to, so I2 is equal to IN. Because this current here, the short circuit current between A and B matches exactly with I2. Okay, so now comes this added step where we actually have to use what was connected between terminals A and B. And so now let's draw our equivalent Norton circuit. We have a current source. We have our Z, I call the ZTH. I really should have been saying ZN, but they're equivalent. And then we have our load here. The load is what's in between A and B, which is 10 minus J5. So let's first of all put that in. This is our ZTH, which is 3.18 plus J 0.71. It's over here. And our Norton current is 8.39 angle negative 32.68. Okay. So now we can use, we're interested in this current here. We're interested in how much is flowing from A to B. This is A, and this is B. So we're interested in this current. And so we can simply use current division to express I naught in terms of IN and ZN. And when you, and I'll spare you of the math, the complex math, the result of this complex arithmetic is 1.97 with a polar angle of negative 2.1 degrees. All right. I won't ask for questions. I don't think there'll be any. Okay. Let's tackle this practice problem here. Let me just duplicate this. This, get rid of this. Okay, so we are asked here to solve for V naught, which is the output voltage of this op amp, and I naught, which is the output current. And so first thing to do here is to look at where you're going to apply your KCL. So there are two nodes here that are very important. This here, we're going to call V1. And this here, you may be tempted to call V2, but it's actually equal to V naught. Right? And the reason it's equal to V naught is because V naught, because of this follower configuration, V naught is the voltage over here, which we know from the ideal op amp assumption is also the voltage over here. So I'm just going to call this V naught. And I'm going to apply KCL here and here. And I will indicate the directions of my current arrows as such. First thing I'm going to do is KCL at node 1, and KCL holds equally for phasors that represent complex quantities. So Vs minus V1 over 10,000, I'm going to express it in engineering notation, is equal to V1 minus V naught over and this is where you have to put in 1 over J, call it W times C, plus V1 minus V naught over 20E3. So this term belongs obviously on the right side. And the important variables here are that W is equal to omega is equal to 5,000. And so we're going to plug in 5,000 for omega, and the C, I should have indicated that this, I'm going to call this C, and I'm going to call this C2. And so, first of all, let me make sure I got that right. Oh yeah, and the other thing that I need to write down is that VS is just equal to 2, angle 0. So let me actually expand this out. So this becomes 2 minus V1 over 10,000 is equal to V1 minus V0 over negative J, and omega times C inverted is going to become 20,000. Trust me. And then the third term here is V1 over V naught over negative J, also 20,000. So this here is just when you apply the values for omega and C and Vs, you get this equation. And so that is going to simplify to V1 times 3 plus J plus V naught times negative 1 minus J is equal to 4. Just multiply both sides of the equation by 2, or by 20,000 rather. Okay. Then KCL at node 2 is even simpler because we just have one current flowing in and one current flowing out. V1 minus V naught over 20,000 is equal to V2, or V naught rather, over 1 over J times omega times C2. C2 is this capacitor here. And that simplifies to over negative J 10E3. And the equation that we're left with is V1 plus V naught negative 1 minus 2J, or J2, is equal to 0. And when you solve these equations, you get that V1 is equal to 1.49 angle negative 26.57, and V naught is equal to 2/3 angle negative 90. So now we have a solution for V naught, but we are also asked to find I naught. And so I naught, oh, by the way, I could usually want to express this. If the input is given as a cosine, then you should express the output as a cosine as well. So V naught of t becomes 0.66 cos 5,000 t minus 90. And then to solve for I naught, so I naught is the current flowing here. All of it has to go to the feedback path because of this follower configuration. There's no current here, which means there's no current here or here or here. So all of the output current of the op-amp takes the feedback path, which means that we can use Ohm's law between this node and this node. V naught minus V1 over 1 over J times omega times C. So that becomes V naught minus V1 over negative J23. And that gives us a very small number, as you would expect with an op-amp current. So this becomes 6.66 times 10 to the negative 5 with an angle of minus 90. And so I naught of t becomes 66.67 sine 5,000 t microamps. This is a microamp. Okay. Moving right along to the last problem of the course, I would have much rather had the satisfaction of doing this in the class. We will do it here. Just going to set up the slide, give myself more room. Okay, we are asked to obtain the closed loop gain and the phase shift for this circuit. Oops, did not want to do that. Cover up the answer. Okay, so this is a non-inverting amplifier, first of all, because the input is connected to the plus input amplifier. And so the gain is equal to, we're going to call G, is equal to 1 plus ZF over ZI, where ZF is the feedback impedance. So all of this is ZF. And this is ZR, or ZI rather. Okay. So we need to divide the total impedance of this parallel circuit, or this parallel branch, divide by this one and add 1. So the first thing we're going to do is calculate, simplify ZF is going to be the parallel combination of the capacitor impedance and the resistance. So that's going to be 1 over J times W times C times R. And that's going to be equal to R over J times W times C divided by 1 over J times W. This is going to be hard to write. This, right? So this is one fraction divided by another fraction. And what you will see is that this simplifies nicely to times R over J omega times R times C plus 1. So we need to divide that by ZI. So the gain becomes 1 plus ZF over ZI is equal to 1 plus 1 over J times W times R times C plus 1. And that becomes equal to 2 plus, these parentheses, 2 plus J times omega times R times C over 1 plus J omega times R times C. So all we need to do now is plug in the values for omega equal to 1,000, R is equal to 10,000, and C is equal to 1 E negative 6. And when you evaluate all that, I promise you, you will get the following number in polar notation. And therefore, the closed loop gain is equal to 1.015, and the phase shift is equal to negative 5.6 degrees. Okay, so that wraps up the course. I hope that this video helped. I will look forward to seeing all of you guys on Monday. I was going to say something about the exam, but I think I've already said everything in the lecture. Again, I hope this helped. And don't forget to subscribe to my channel.